Hello everyone, my name is Ina Farouk. I am the geotechnical application engineer for Oasys, and today we will be running our first exclusive and demonstration-based webinar on our piling software and piling suite for single piles. The objectives of today are to familiarize you with the programs Pile, Alp and AdSec, and that would be through our theory and just a brief discussion of what the software does. I'm then going to set up a pile analysis in Pile, ALP and AdSec. So we'll look at a single pile, give it a look at the capacity analysis, determine its length, and go into ALP, do some apply a lateral load and see the way the pile is performing, and then finally look at a section analysis for the pile. And I will help you appreciate how the Oasys Piling Suite has been used in industry by looking at one or two case studies. There are other webinars that cover other aspects of pile design. One would be the Eurocode 7 ultimate limit state design. The other would be, for example, looking at piles as part of an embedded retaining wall or through, or analyzing pile groups. So there are a number of options out there, and if any of you would like to discuss it personally, then please do pop me an email. Otherwise, look at the webinars that are available. So let's start off with what is a single pile. Well, a single pile is a pile that when loaded does not have any interaction effects with the adjacent pile. Otherwise it starts being defined as a pile group. And the spacing between the piles will depend on the solution model and the ground conditions. So for example, depending on the type of pile here, as you can see there are a number of piles. There's a precast H pile here. We've got, for example, under-ream board piles here. Depending on the type of pile, there has to be a certain distance between these piles to define it as a single pile. Now, for any kind of single pile analysis, we can use any of these programs depending on what you would like to design for the pile, or use them all together, and that's what I'll be doing today. The first program is Pile, which gives you the vertical capacity of the pile, and from the vertical capacity, the designer can calculate the required length of a pile. And then there's also settlement analysis. So this is based on Matz and Poulos, and what it gives you is the required settlement. And say, for example, you wanted to limit the settlement for any reason, or limit the settlement because you've got a utility nearby, Pile would help you calculate that. With ALP, ALP looks at the response of the pile to any kind of lateral load, any displacement, any moment, any restraint. So based on what you apply to the pile laterally, ALP will calculate the maximum moment on the pile, and it will give you information about the cage length. Now, something like the moment is very important because it helps you design the actual section of the pile. So for example, how much reinforcement do you require in that pile? And that's where AdSec comes in, because AdSec is the non-linear concrete and composite section analysis. So what it allows you to do is look at a section of any kind of pile. Maybe you want to put some rebar in or something like that, and it will give you, for example, information on stiffness and cracking. So we're going to start off today with Pile. Pile is a program which gives information about pile capacity and settlement. And I'm going to split it into two sections. We're going to start off with pile capacity and run a capacity analysis. So the pile capacity aspect of Pile is that it determines the vertical load capacity of a pile for different pile types, different pile materials, a range of pile lengths, numerous soil layers, site-specific groundwater conditions, and different factors of safety or design resistance. And this includes Eurocode 7. So why should you use it? We know, for example, I'm sure when you were at university or when you were designing first, you might have been using a spreadsheet to calculate or to calculate the capacity of a pile. Well, for a large company, for example, a lot of spreadsheets with a lot of changes often equal a lot of errors. So this really helps the QA process. It calculates shaft and base capacity as well, so it can deal with total stress problems and effective stress problems. So, for example, we can look at undrained parameters for clay, combined with a problem which, for example, clay overlying some shale or some some sort of drained sand, and it models plugged and unplugged behavior for tubular and H piles, so slightly more complicated sorts of problem. It can incorporate negative skin friction, and it's really simplified the design to EC7. So any kind of factoring or Eurocodes, it really simplifies it down because it's a click of a button and you can factor to design approach 1 or any factors that you put in. In terms of capacity, the capacity section, what you get is you get the ultimate and allowable capacities, which eventually gives you the length of the pile, and also you get the tension and compression capacity. So you have to input the pile section, under ream if it's there for you, and also the soil parameters. So I think we're ready to go into the program. So I'm just going to look here and start up pile. So I'm going to start a new file here, and when I clicked on new, a number of options come up in the gateway, which you can see to the left here. So we've got titles, and in the title section you just fill it in with information about, for example, your particular project or what you're doing. Now it's important that you fill this in properly, the reason being that if it's not filled in, this doesn't come in. For example, this kind of information comes in your outputs, in a graphical output or tabular output, so it helps a lot with checking. So that's something you should be aware of. In terms of units, we've got a number of units here, and we've got a number of options. So depending on where you're designing or what country you're designing in, the Oasys Suite offers you all those options. We've also double-clicked on analysis options, and we've decided to do a capacity analysis only. So in terms of effective stresses, I want them to be calculated, and where our particular problem is looking at elevation. So for capacity data here, I'm going to look at working load. Okay, so in terms of the global factor of safety, I've got 2.5. It is worth actually mentioning at this point, before I go on, that there is also code-based options and design resistance options here. So as you can see, we've got Eurocode 7, we've got the Indian standards as well. So there are a number of options available to the designer, but I'm just going to go with working load here. So I've put the global factor of safety in. I'm now putting the partial factor of safety in. I'll keep this at unity. I think we'll not limit the pile stress in either case, either tension or capacity, because we'll just go full out, and I won't worry about shaft skin friction either. So I've finished with this. Okay, I'll keep that at unity. Okay, so we'll go on to the pile properties and information about the pile. So as you can see here, there are a number of options. So say, for example, I went into H pile and clicked next. I can define the H pile itself, but I'm just going to go with the standard CFA pile. So if I click on solid circular without under ream, we're then going to go, we can have a look retrospectively, for example, at a pile. So I can have a look at a single pile length. But if you're designing a pile, it's quite useful to look at a range of pile lengths. So I'm going to go here between 5 and 35. And we'll have a number of increments. Now, the number of increments means that there'll be more calculation points which are outputted in your tabular output, for example. And so that would help with the analysis of the pile. Increment size 30. Okay, so as you can see, we've got what I've done is I've increased the number of increments to 30 here. What we previously had in terms of increment size was every 3 meters. I've increased it to 30, so we have an increment of every 1 meter. And the pile goes to the top. And I'll put a 600 mil CFA pile in here, but I will show you that you can actually compare different diameters of pile as well. So if you really want to look at different types of designs, you can do that. So say, for example, if I put 0.7 here, I can have a look at a 700 mil CFA pile. And again, there are a number of options available should you wish to use them. Okay, so I think we're ready with that. Now we need to put our material properties in. So I'll double click on this, click on undrained materials. I'm going to tab. And the reason I'm doing this is we've got a default option at the top here, and it keeps that default option. So I've tabbed into the bulk unit weight, but in terms of the soil strength, we'll start off at 60 and go up to 260. Specify alpha at 0.45. We'll say no limiting value. Yes, and C should be specified, and I'll put a value of 9 in there. Okay, again, no limiting value. Okay, so this is say, for example, clay. So I'll put stiff clay 20, 260. Keep it at 260, alpha specified. I can type in equals to copy everything from above, so that's exactly what I'm going to do to save myself some time. Okay. Okay, so I think that's all done. I think we're good to go. So that's done in terms of undrained material. I might actually call this clay to avoid any confusion. Okay, and then we're going to go into some drain materials. Maybe I'm going to put a make ground at the top. And we'll say the bulk unit weight of 20. I'll use the earth pressure skin friction computation method with a delta of 25. A K value of say 0.8. No limiting value again. NQ specified at 50. Okay, and again no. Okay, so that's done. So we've put all the material properties in, but now we need to actually give a definition of the stratigraphy. So I'll start with 8 meters OD made ground. We'll say no to contributing to negative skin friction. 0 meters OD clay. Undrained one. I'm sorry, I didn't press tab in the previous option, so that's why it just came up as that. And we've got minus 25, so stiff clay. No. So the clays may possibly contribute to negative skin friction, so it's up to the designer as to what to do for that. But if you look down here, you can see that we can actually add profiles along the way. So you can we can compare more than one soil profile, and that also applies to groundwater profiles. But I'm just going to put one in here. Simplicity. Okay, so one groundwater profile and one soil groundwater profile map. So as you can see, there are a number of options that you can look at, and this means that instead of having to copy your files, you can do it all in one file. Okay, so I think we're good to go. At this point, you should really save your file, but I'm just going to analyze it. Okay. Okay. So here we've come to the graphical output. So I'm going to look at the results in compression and tension for working load. So as you can see, we've got here the capacity line and the tension line, the compression line and the tension line. So as you can see, compression is the line that will have the biggest impact. So if I look here, I've got the capacity. If I switch this off. So we've got the capacity in kilonewtons here. This is around, say, 2,000. And I'm interested maybe in around 1,000. So by I, I'm saying that the capacity is maybe around what? The length of this pile will probably be around 17, 18 meters, say, just to be conservative. So if I double click on tabular output and just click on the capacity results. So if I look at this particular results in compression, allowable capacity for around 1,000 is 16 meters. So that looks fine. As you can see here, we've got at 16 meters below. If at 16 meters OD, we've got minus 16 meters OD. We've got 1,000 kilonewtons, is it? Yeah, so I think that should be fine. So at minus 16 meters OD, that's where we should be cutting off this particular pile. And let me just check the soil profile here. Yes, okay, that's great. So we're done in terms of capacity analysis. And as you can see, we've got quite a useful graphical output for picking out anything, but we can also check with our tabular output. And if you did want to, for example, export this and do any kind of further analysis, what you could do is you could click on File, and export results. So if I double click on the tabular output, click on File, Export Results, if I choose CSV, I can actually save this as a file that would open in Excel, and I could do some further analysis in it. If I did also want to print it out, as mentioned, everything that comes up in the title and units, box or table is actually output in the printout. So it's important that you fill it in appropriately. Okay, so I think we can now move on to the settlement section of Pile. So if I go into that. Okay. In terms of settlement, what Pile does is it uses theory by Matz and Poulos to split up the pile into a number of compressible pile sections, and then it does an elastic analysis where it looks at where it uses the Young's modulus of the soil above the pile toe and below the pile toe and the pile itself, and it looks at the continuum of the soil around the pile as well. So that's how we get settlements out. In terms of outputs, it outputs a settlement and the stresses based on your dimension, stiffness, negative skin friction, and heave. So I'm just going to go into a demonstration now. So now I'll go back into analysis options and I'll click on settlement as well. Okay, that's absolutely fine. So now I'm going to put the settlement data in. Okay, so I'll say there's 20,000 or 40,000. Okay, the rigid boundary is a point where settlement goes down to 0. So I'm going to leave that at quite a high number. Number of pile elements. Okay, so number of increments. I'll keep a number of increments quite high, which means that the pile has actually been split into a number of parts, and that means that we'll have a more accurate value for settlement, but I only want one output, so which is why I'm saying print increment results at a rate of 1 for every 1,000 increments. I'll say increment type for load. Okay, I think we're ready to go. Now we need to put in information for applied loads and displacements. So I'm going to say, I'm just going to say load 1. I'm going to have a load at the top of the pile, say 150 kilonewtons with no soil displacement. And I also want to find out, say for example, I've got a utility at maybe 1.5 meters away from the center of the pile, and I want to know the settlement for that because there's a limit on it. I'm going to put in displacement radio 1.5. So I think we're ready to analyze. Okay, I don't want to look at the capacity results this time, but I'd like to look at the stresses and the displacements. Okay. So this gives, as you can see, because we've got 1,000 points, there is a number of points there's a number of points showing on the tabular output, which is why we've got such a big tabular output here. But this is actually quite helpful if, for example, you wanted to do a more detailed analysis in Excel, you could do so. In terms of graphical output, the settlement results are in this section here, which is the most to the right, which is the rightmost bar on the output. And as you can see, we've got our capacity analysis, or we've got the capacity analysis in the middle of here. So we can look at the shaft skin friction and the limiting shaft skin friction. So we've got these values here. And as we press this plus button here, we can go down and have a look what happens as you increase the length. So our length was around 16 meters. So this is the length that we're most interested in based on our capacity analysis. So if I switch that off and look at the stress, is the stress acceptable? So we can just check that and see. And finally, we were very interested in the displacements, both of the pile. So we're getting a very low displacement of the pile, so that's great. But we're also interested in the soil displacement. So the soil displacement is less than, it looks here, maybe by eye, I would say maybe 0.4 mil, maybe max. So we can have a look at the tabular output for a more detailed output of that. So say, for example, if the utility is down at minus 10 meters, we're actually getting a displacement of 0.25. If that's acceptable for the utility, that's great. If not, we have to look at the design of the pile. So that gives you a little bit of information as to how how this program works, and I think that gives you a pretty good understanding of what's going on with pile settlement analysis. We're now going to go on to the developments in Pile. So there are new developments coming up. There is a very new version of Pile available, which I think will be released as well over the next 2 or 3 months. And it's actually got some cutting edge techniques in there with regards to thermal loading and cyclic loading. So we're going to be putting some new settlement curves in there called TZ curves, which allow the user to look at settlement, apply thermal loading, and look at cyclical thermal loading or mechanical loading. The user will also be able to look at stage loading. So, for example, something similar to a program like Fru, where you can apply loads at different stages and see the kind of impact that that would have on the pile. So this is something quite new, and it's quite exciting. And I think we have an MSc student looking at this now, so hopefully we'll be presenting on that by the end of the year. So that's completed our little introduction to Pile. Now going on to ALP. So we've looked at the capacity analysis and settlements due to any kind of vertical loading, but what happens due to horizontal loading? That's what ALP gives us. So ALP calculates the earth pressures, horizontal movements, bending moments, and shear forces based on the lateral loads, moments, or displacements, the lateral and rotational restraints, and the soil load and deflection behavior. So in terms of theory, what ALP does is it works in a very different way to a program such as Pile. So it models the pile as a series of elastic beam elements and models the soil as a series of non-interactive, non-linear springs. And the forces and moments are applied at the nodes. So as you can see, we've got the nodes here, and you can, for example, apply a strut or apply a force at the node. And the soil response model is either elastic plastic, or you can model non-linear behaviors such as PY curves, either generated PY curves or, for example, a user input PY curve. In terms of the theory, you could model, for example, you could model this pile as in an elastic plastic way. So that assumes elastic behavior until the passive limit is reached. But unfortunately, it's very simplistic, and it's not really the way the soil works. So, for example, if you've modeled the soil in this way, it is difficult to model accurately. And so for that reason, ALP provides the user with PY soil models. So soils are inherently not elastic plastic, and there are a number of curves available from theory for soft clay, stiff clay, sand, different types of rock. And you can either use publications yourself or site investigation data to actually define your own PY curves for different strata as well. So this is quite a good feature that ALP provides, and it helps you model the response of the soil much more accurately than an elastic plastic model. You can also look at cyclic loading. So that's why ALP is very popular, say, for example, for looking at projects where you've got wind turbines, or maybe you're looking at wave loading on the pile. So these kind of things are very popular with ALP. In terms of the outputs for ALP, each increment is listed, so we can have a look at the effect of a number of different loads. It's easy to check using the graphical output, but we do have much more detailed tabular outputs, as with Pile. And it gives you bending moments and shear forces, which are used in the reinforcement design, which is what we're going to use in AdSec today. So for the ALP demonstration, I'm just going to open up ALP. So as you can see, I'm just opening up ALP here. If I click on New File, the wizard opens up. So I'm going to say webinar example here. Okay. It starts off with elastic plastic option, and I want to input by level. Okay, so the pile bottom, if you remember, was minus 16 meters. The pile top was 8 meters. The effective width is at 0.6. We've got an EI, we'll say for the time being 40,000. I'm going to show you a nice way of calculating EI values now. In terms of applied load, we'll say that it's at the top of the pile. Force of 150 kilonewtons for the time being. We've got the soil top level, we'll say at 7.5, E value of 2000, unit weight of 20. Okay, I think this is all good. Excellent. So I'm going to say generated PY curves for this particular problem. We're doing a static analysis. We can look at loads only, and we'll input the levels. What the section wizard is referring to is that we now, within the sections option of the gateway, you can actually calculate your EI value based on inputting your section. So I'm going to use Eurocode 2, but as you can see, there are a number of options available. But Eurocode 2 will be fine for us. And I'll click on Apply. Okay, so I think we now need to put in the information about the soils. So in terms of soil data, we'll start with the sand at the top. Okay, there are a number of options for sand here. We've either got the REIS or the API. I'll choose the API, which is the American Petroleum Institute publication. We're using a unit weight of 20 and 530. In terms of the soft clay, it was at 0 meters OD. We'll say soft clay here. Got 20. And the E50 value is 0.02. Now you might be wondering, what is the E50 value? And this is why the help manual is very helpful, because as you can see, I've opened the help manual here already, and under method of analysis in the PY soil model section, you've got information about each PY curve, and within this you can find out information about the E50 values as well. So all of this is available to the user, and it's something that you should definitely read and check through. So for example, we have different parameters here, K1 and everything else, and all of the information about this is available within the manual itself. So I'm going to use a value of 0.02 based on information from the manual. The CU at top is 60, DCU by DZ is 8, so it goes up to 260. And then minus 25. This was stiff clay. 20, 0.01, 260, 0. Okay, that's done. Okay, so that's the soil data put in. In terms of sections, I did put in the wizard that, I had just had an explicit section, but what I'm going to now go for is under input type, I'm going to click on generated. And once you do that, it opens up the section wizard, which can also be opened up with this wizard sign here in the icons at the top. Okay, so for this, I'm going to call it CFA circular with rebar. Under pile, I'm going to put the material. Under profile, I'm going to make sure it's circular. Okay, and 600 mil. Finish that off. In terms of reinforcement, I'm going to click on add 20 mil. Say we've got 8 bars. And I'll put the point on the circle. Okay, so if I click on OK for this, you can see that this is looking reasonably realistic, and that's pretty much what I want. So now if I click on OK, that looks good. Okay, so it's calculated the EI value for me, as you can see here, based on my generated section. So, okay, the section details have been given. The pile properties are now done. Let's check the soil data. Okay, applied loads and displacements are in there. Okay, at this point, as I mentioned many times, you should save, but I'm just going to run the analysis. Okay. I need to read that carefully. Soil data table refers to node 0, which is inferred. Okay. So I made a very common mistake here, which is where this soil data refers to node 0. Strange. Okay, so we've got 8 meters, 0 meters, and minus 25. Node level is 8. Okay, the reason is the rigid boundary must have been, I must have input the rigid boundary at the wrong level. So minus 16. Okay. So it's only wanting to go to the bottom of the pile basically, or just below that. So we'll have a look and see what we're getting here. So it only goes up to minus 16. So as you can see, it's not necessary to go further than that. So if I go to solve data 0 and I say minus 15, that's not correct. I'll say minus 17. Okay, so this is giving something. So obviously I've just gone beyond the rigid boundary here. Okay, so with this data input now, we've got the analysis options. So if I look at the graphical output, as you can see, most of the pressures are occurring within the made ground. So if I click on look at the displacement, as you can see, the displacement is not that high, and it's within the made ground. If I look at rotation, there you go. There's a little bit of rotation at the top, but nothing to be too concerned about. I am interested in bending moment and shear force. So shear force, as you would expect, is 150 because of the loading that we've got at the top here. And bending moment, we've got a bending moment here around maybe 200. So if I go to tabular and click off everything else. Okay, and just look at the results. So for the maximum moment, yeah, we've got, so the extreme value so far, the maximum moment here is 207 kilonewton meters, so that's just about right. So that's the value now that's going to have to go into AdSec, and we're going to have to design section for. But as you can see, the bending moment here is cutting off around 0 meters, or say even maybe about minus 3 meters. So the best thing to do would be say that the cage should be going down to maybe minus 5 meters to be conservative. So that it just gives you an idea of the cage length as well for the pile. But as you can see, we really don't need to go right down to minus 15 meters. So I think now we're ready to move on to looking at the section and analyzing the section. So the ALP demonstration is complete, and we're going to go into AdSec and look at nonlinear concrete and composite section analysis. So as you can see, there are a number of sections that you could create in AdSec. Some very simple, like a pile, but you could do much more complex design in AdSec as well. And what AdSec does is it carries out a strain plane analysis for any given section, and so it solves the equation for strain basically. It offers two options: a ULS analysis, which looks at the ultimate strength of a section, and it uses material factors or strength reduction factors. But the SLS analysis looks at the section in its normal working state, and it allows for long-term analysis and short-term loading. So, for example, if you wanted to analyze the section for creep, you could put a factor in and see the way it behaves in that manner. So the kind of outputs you get are section capacity, stiffnesses, and cracking. Based on the section that you input reinforcement and loads. And so this is just an example of one or two of the graphs, which we're going to go into now. So for example, you've got this load moment, the axial force and moment graph, and you can have a look at how your specific case fits into that. So as you can see here, we've got a number of cases here, and for example here it would be acceptable within a certain axial load, and this would be acceptable for this load case 1 would have been acceptable for all these axial loads, but load case 2 is only acceptable for certain axial loads. So it gives you a little bit of information there. And as you can see, there's serviceability information as well. So we've got the stiffness and the yield graphs, and we can have a look at moments where yield has occurred, and then get yield stiffnesses and fit that back into ALP. So as you can see, there are a number of options available from AdSec in terms of pile design, giving you crack widths, nonlinear crack sections, stiffnesses and capacities, regular and irregular concrete and composite sections, and ultimate and serviceability condition checks. So I'm just going to set up a quick problem in AdSec. So if I click on the AdSec icon, And I'm going to create a new section, so the wizard's going to open up for me. I'm just going to say here, for example, webinar example. Okay, I'm going to choose the Eurocode 2 because that's what we had used within the ALP analysis, and we've got to be consistent. Click on next. Okay, I'll say circular CFA. Okay, I'll put this down to 2025. If I click on section, we get into a similar wizard to that we had gone into in ALP, so diameter 600 mil. Okay, and finish. Okay, and aggregate size 20 mil. Okay, now we need to put the reinforcement in, so I'm going to go for a column arrangement. So we'll give a 75 mil cover to the links. We have code cover options here as well if you want to go a bit further into it. If I remember the link down, 12. And now we're going to go into the bars. So if you remember, we had 8 bars within there with a diameter of 20 mil. I've got one ring and we've finished that. There are also a number of options in terms of adding more complex type of bars. So for example, you could put a LiDAR bar in there or anything else, and it's got the wizard in there. So we can finish with that, and if I open this up now, you can see our section. So this is looking great. It's 89% reinforced, 0.89% reinforcement. So now we need to analyze this particular section. So under loads, we've got load titles. I'm going to call this load case 1. I'm just going to analyze it for one particular case. So under loading, for this one, I'll say section force. I'll put the force as 150 kilonewtons to be consistent. And also, if you remember, our moment was 200. So I'll say, yeah, so we'll say 200 here. We could have factored this moment as well. So depending on what kind of design we're doing, you might want to factor this and give a bigger moment. Okay, and we now need to put together the analysis cases. So we've got the loading for the ULS case. We're just going to say load 1. We could factor that there, but we're not going to for this. And you could, for example, combine a number of loading factors if you wanted to as well. For the SLS case, I'll look at long term. So I'll say 0.75 L1 for the creep. Okay, I think we're good to analyze now. So we can look at the strength analysis. Okay, look at the general results. So for example, under strength here, we can get moment capacity. So if I go down and have a look at the moments, you can see here the moment capacity is around 0.86%. So it's working, and it's working well. Under ULS loads, we've got the loads here, and we've got all the information for the loads here. For the NM graph, for the load moment graph, I'm just going to call this, we don't need to call it anything for this particular output. We'll put MYY in there. And we can actually plot our load case within this problem. So if I go in here and click on load points, okay, click on OK. As you can see, this load case doesn't look great because it's actually very close to the envelope here of load and moment. So that's probably not fantastic, and we might have to reassess the reinforcement design. If I look at moment interaction, say put an axial load of 0 and 300 in there and have a look at how that's behaving. Okay, we'll plot this with the load point within there. Okay, and the load case looks good actually. That seems fine. It'll be interesting to see what happens if I plot a slightly higher loading. In terms of SLS loads, we can do an SLS analysis and get the crack results out. So that's all available. And then we've also got the serviceability analysis. So looking at 0, 500, say, for the axial loads. If we do the analysis and have a look, you can see we've got different graphs here. So for example, what's happening here is we're getting a stiffness, and as we increase the moment, you have yielding, and you've got the you've got the yield stiffness here. And so this kind of value for yield stiffness, say for example we're getting 20,000 kilonewton meters here, this kind of value is then fed into ALP. So for example, if I go back into ALP and go into sections, I could put a yield section in here, an explicit, and maybe put 20,000 in here and see how it's behaving in that particular yield section. It can be a slightly iterative process, but it does give you a very good and coherent design. So as you can see, we've used 3 programs in a very different way to look at different elements of the pile, but we've come up with a holistic design of a pile. So it's something quite all-encompassing, and it does give you a very good design of a single pile. So I'm just going to show you how different designers have used these programs in conjunction to design a pile. And I'll start off with a problem given to us by Burn Luby Partners. So this is particularly designed for a level crossing in Kilmarnock. And the piles had to resist 830 kilonewton uniaxial compressive load. But there was also a transverse horizontal load on the pile of 170 kilonewtons and rotation as well. So as you can see, we've got the cage here and we've got the pile. And so for this particular problem, the cage length was calculated using ALP. So what they did was they looked at the bending moment, and they've said the cage length is it comes to 0 around 6.5 meters below the top of the pile. So that's where the cage length should go down to. It's also given, for example, values of maximum shear force and pile head movement, which is important. But it's in conjunction to that, as with the problem that we looked at, we've got maximum bending moment for the pile, which is 145 kilonewton meters. So then what the engineers had done is they had looked at a section, carried out an AdSec analysis, and they said, okay, based on this section, for the loading that they've got, so if you remember the loading was 830 kilonewtons, so from the loading of 830 kilonewtons here, if you look at this particular envelope, the maximum allowable bending moment is 280 kilonewton meters. So if you remember from the ALP analysis, ALP had generated a bending moment of 145 kilonewtons. So they factored this up by 1.5 to get a maximum bending moment of 218 kilonewton meters. So this is within the allowable bending moment, so it's okay. But say, for example, ALP had outputted a bending moment of 200, it may have been 250, it would have probably been outside, and then we might have to reassess the design or put in more reinforcement. So it gives you an idea of how designers are using the software. A very interesting problem was carried out by some Arab engineers, and this was at UCL Hospital. There were a lot of constraints on this particular geotechnical project. So firstly, there was a very close proximity to another structure. And there are also limits on space restriction and therefore what could be installed for certain walls. So what the engineers had to do was propose a design of a basement retaining wall next to piles for the Rain Institute. And so what they did was they carried out basement retaining wall design using FRU. And when they carried out the FRU design, they outputted horizontal ground movement and vertical stresses. So the horizontal ground movements were fed into ALP to then give information, for example, like moments, which was then used to calculate whether, for example, the actual basement construction was affecting the Rain Institute pile. So an analysis was carried out in AdSec on the Rain Institute piles. But also, for the Rain Institute piles, an analysis was carried out in Pile using the vertical stresses output from FRU. This gave information about axial stresses. And the axial stresses, again, were fed into AdSec. And so what this meant was that ALP, Pile, and AdSec were used in conjunction to analyze the Rain Institute piles. And again, cracked EI was output from AdSec, and there was slightly iterative design between ALP and AdSec. Now, this may look onerous, but I actually spoke to the designers about it, and what they said was this didn't take very long, and the reason was that because of the gateway and the tabular output between all of these programs, it was quite easy to copy and paste between them. So it wasn't particularly difficult to run any of this, and it took less than half a day to run this whole analysis. So here's just an example of the output with the skin friction, for example, and the displacements and so on and so forth. So just to summarize in terms of what the programs do, Pile, you should now be very familiar with, carries out a vertical capacity analysis and settlement analysis. So you output the required length and the pile settlement. ALP looks at lateral loads on the pile, and it gives you information about moment and cage length. Now the moment information from ALP, as well as any loads, is fed into AdSec, which looks at the section of the pile, and it gives information about stiffness and cracking. So in summary, in terms of the objectives of the webinar, we have given you information about theory, so we've covered section 1. We've set up a pile analysis in Pile, Alp and AdSec. So I've looked at a pile, I found the length of it. I then went and checked the settlements. I gave that information, I put that information into ALP. We looked at the bending moments that were output from that, and then based on that, we designed the section of the pile. So we did a holistic design of one pile. And I also showed you some case studies to show you how it's being used in industry. In terms of what to do next, hopefully this has given you the taste of how powerful the software can be. So you're welcome to try the step-by-step examples and check out our tutorials, which are available via the support section of the product pages. Look at the bottom of any page in the Oasys website, and you can see YouTube there. And if you type in Pile, it'll pull up all the Pile tutorials, anything to do with Pile theory, anything which is available on video. So you might actually pull up, for example, something interesting on GSA Raft and looking at Pile group design. So it'll give you all the options that are available. But more than anything, we're very interested to hear from you. So please do email us with any queries, or if you want to find out how the programs work, telephone us, and we're happy to talk to you face to face as well, so arrange a meeting.